This is the 7th of the videos in the series in which we're looking at the question of a theory of everything and what's involved in that. And we're at the stage where I think where we can start to get into something rather more interesting than just talking about laws and dimensions and variables. I'm going to talk about the energy model. Our model, full title is a mathematical model. The model, a mathematical model, is an imaginary system or structure, working structure, but imaginary, that is governed by the same laws as the system that you're studying, and can use the same equations. But you tend to simplify them considerably. My first encounter with simulation was when I was asked to design a simulator for a nuclear reactor. And you can't take everything into account in the case of a simulator of a nuclear reactor. But my purpose was to study the kinetic performance, and so I had a set of differential equations that describe how the neutrons are multiplied in a nuclear fission chain reaction system. And later on I simulated businesses. Again, you didn't take into account everything, just what was most important. And similarly with the universe. And that's why I've taken this sphere, which we're going to use to simulate or to represent, to be a model of a two-body system such as the Earth and the Moon. And if you can imagine the Earth in the center of this sphere and the Moon on the surface. And one of the things that we discussed, and I'll go into this in more detail later, was that the total separation between the two bodies was constant. And as you can see, the separation between the surface and the center of the sphere is constant. So if you think of the Earth as in the center of this sphere and the Moon is on the surface, and it must stay on the surface for its entire life. It's there when it was first formed. When it left the Earth's surface, it was on the surface of this energy shell over nearly a third of a million miles away from the Earth. How can something be a third of a million miles away on the surface of a sphere when it's just leaving the Earth's surface? Well, the answer is because this is not representing just space. It's representing kinetic energy too. And the separation between the Earth and the Moon, when the Moon left the Earth, was such that it was already, in terms of energy, it was on the surface of this sphere. And it's been there ever since. We'll talk about how it got into a circular orbit later. But this is as it would be now. If you could see the sphere, you'd see the Earth in the center and the Moon in a circular orbit that's smaller than the size of the energy sphere, but it has a constant energy now because it's on the surface of the sphere, and it has a constant kinetic energy or constant momentum because it's going around in a circle at a constant velocity of just over 2,000 miles an hour. So that's the model now we're going to use, and we'll start working with that. One more thing, and that is that what you're seeing here has 3 dimensions of space, but in fact there are something like 9 dimensions altogether, and I'm going to be talking about how you get 9 dimensions into a 3-dimensional body. We're only going to look at 3 dimensions at a time, and the other dimensions we're going to freeze. It's like taking a cross-section of something in the way that an architect will cut through a house and say, here's a side elevation of a house in the center showing the rooms, but ignoring the walls that are either side of that. You are freezing one dimension, saying it doesn't exist, or it's small, so small you can't see it. And then you can see what was visible. And here we have 3 visible space dimensions. But I'm never going to use 3 dimensions in discussing, well, yes I am, I suppose. No, I'm not necessarily, we'll see as we go along. So let's put this down, and I'll throw that over there, and draw some diagrams to represent this system. Remember that we said that the total energy between two bodies was the sum of what represents the kinetic energy and what represents the potential energy. So this represents the potential energy, this represents the kinetic energy, and this represents the total energy. But these are lines, and so I'm going to refer to them as R0, which is the length of that separation. It's a length, just as that ball had a radius of a certain length, and that's the radius of the ball. This is the length of the potential energy, which actually is the separation in space. And we're using that as our way of representing energy to say, I call it the energy equivalent length. And the length between the Earth and the Moon in space represents the potential energy. It's not a linear relationship, but you can say that when it has a certain separation in space, it has a certain potential energy. But there's also a separation that represents the kinetic energy of the Moon. And if you make these all into lengths, you can draw a diagram like that. And this is the radius of the Moon, Moon's orbit. Now, what does this radius look like in reality? It's not a straight line, it's the sum of several lines. So I'm going to draw it larger so that I can give you more detail. The way in which you get several dimensions into a three-dimensional sphere. Let's say that this is the total radius. This is the radius of the sphere, and a part of that is space, and we can draw that like this and say that this here is kinetic energy, and this is space, we'll say, and this is what I call the x dimension, which represents kinetic energy. I'll show you mathematically how it does that later. Now, space, you see, has 3 dimensions to it. So we can say, oh, well, this space is the sum of this space here, which is, we'll call R1, which is the space, perhaps, to the north. And this is the space that's to the east-west. But there's also a 3rd dimension, and so we're going to break this one up into 2. And as long as you do that with right angles, you can do that. So this is 1-dimensional space, this is the 2nd dimensional space, and this is the 3rd dimensional space. And when you add the squares of these, you get this. This squared is equal to that squared plus that squared is equal to that squared plus that squared, so that squared is equal to that squared plus that squared plus that squared. So it looks rather odd. It's difficult to believe because they look so much larger. But remember, they're squared. And when you have fractions squared, they get smaller. So that the square on this is equal, plus the square on this, plus the square on this is equal to the square on that. Now this represents kinetic energy. Now, the kinetic energy also, a body can move in 3 dimensions. Now most of the time I'm going to talk about the total velocity. Here you notice that the kinetic energy is greater than the potential energy. This drawing would be true soon after the Moon left the Earth, before it got anywhere near where it is now, because the kinetic energy is much greater than the potential energy. And that means it was still moving pretty fast. So this would be an early drawing of the system. Now when they're in a circular orbit, these 2 lines are the same length. But if you want to say, well, in what direction is the Moon travelling? Well, it's travelling partly in that direction and partly in that direction. You see, here's x1 and here's x2. Or you may say, well, it's travelling also in a 3rd dimension of space. So we'll break that up into another 2. That'll be x2 and that'll be x3. And that's no longer x2 here. So here's the kinetic energy in one direction, in another direction, and in another direction. So here we have the velocity of the Moon represent as an energy represented by length. Here we have its separation, the potential energy. So this squared plus, and incidentally, since this squared plus this squared equals this squared, then this squared is equal to this squared plus 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 this squared. And I'm not going to go any further, but there are also time dimensions. And that's where we get 9 dimensions. So there's another one here, part of the X actually, because the time creates a kinetic energy, as Einstein's special theory said, so that we can split this up into another 3 dimensions for time. But this means that your sphere now looks has what I call a crooked radius. If this is the sphere, the radius is actually something like this, a crooked radius. But these all added up as squares, and find the square root, you get the radius, the true radius, which is the sum of the individual the radius in the individual dimensions. So that's where we're coming from when we talk about multi-dimensional spheres. We can't perceive more than 3 dimensions. So we're going, in fact, I can only draw 2 on here at a time. So I'm going to talk about 2 dimensions at a time. Now, as I said, the moon is in the center of the X dimension, which goes this way. This is the total X dimension. This represents the total kinetic energy, which is constant. And therefore, this is a constant distance from the center of the sphere. The sphere as a whole is like this. And the center is in this direction. Looked at from the side, if we look at the total now from the side, that's this one here, this is not in the center, it's here. The moon is going up and around in this direction here, perpendicular to this board. Here I show we're looking at this angle here, and here when we look at this we see this. So here we have the X dimension, and here we have the space dimension R1. And the moon, which is not always there, if it's here, it has this coordinate for distance in space, this coordinate for distance in the X dimension, and that's the total separation. So you see, as it's orbiting now, it's going around like this, so the X dimension is constant, which means the velocity is constant. But the distance from the Earth in space is varying as it orbits in this direction. So this is one view of the sphere, and that's why I did have this here, here where you see, look, this is this diagram. Here, when you're looking at it this way, you see the moon going that way. But when you look at it like this, with a space dimension here, the moon is going up and down. If you look at it from the side, if you could see the moon from the side, you'd see it going up and down. And that's that view there. So that, I hope, will explain something about the model. And I haven't gone into any mathematics. I'll do that, I think, in the next video, because I don't want to overdo my 15 minutes limit on putting videos on YouTube. So I think that'll be enough for now. I've probably got to 15 minutes. So next time we'll talk about the equations that govern this model, and some solutions to them, particularly to show how an elliptical orbit is created. So thank you for watching the 7th video.